Hello everyone. Welcome to the live interaction session on diffusion in multi-component solids. And this is Sachin Kumar, a PhD scholar. Yes. Hi everyone. Hello. This is Sachin Kumar. Welcomes you for the live interaction session on diffusion in multi-component solids. So this is a platform which we will be using for solving the and interacting the doubts on different concepts as well as the problems which is faced in this subject diffusion in multi-component solids. So this platform you can share your doubts with me and with your friends also. So we will be discussing through this platform and we will be trying to get the solution for the every problems. Okay, so today I think we can wait for 2 to 3 minutes for others can join this session. So it's almost 6 and 7 right now. So we can start our session. Here, the course name is a diffusion in multi-component solids, and the course ID is NOC 24 MM17, and the course instructor are our professor Dr. Kaustubh Kulkarni, and this is Sachin Kumar, which will be conducting a who will be conducting a live interaction session with you guys for solving the problems and discussing the numericals which will be useful for the solving the assignment problems. Let's start our. This is the first lecture, first interaction session. So we will start this with a reference book that we will be using in this course. That is a diffusion in solids with a Paul Shimon with second edition. We can use it for the problems as well as the concept clearing session, as well as a diffusion in solids written by Helmut Mehrer, which is a Springer edition. And we will be using a phase transformation in the metals and alloys with David A. Porter and Sterling. So this book is mainly used for the all other subjects also, like for example heat treatment also we can use it, and diffusion also we can use it. And one more book is material science, Porter and Sterling. Yes, this is Porter and Sterling. Yeah, this will be used for the other subjects also and for the basic concepts of diffusion. So these are the reference book. And one more noted point here is, so whatever the numerical problems as well as the concept taught by in the video lectures of NPTEL, that will be more sufficient for solving for clearing the your exam, final exam, as well as solving for the assignment problems. So we will be extracting and we will be solving a similar problems which will be given in the assignment as well as solving in the video lectures. So these are the references book. So if you need any of these books, please let me know, and we will be I will be sending through a mail. So this is a course content of a week 1. Okay, so this week 1 is having a starting a course with an introduction to the course. Yes. So it is started with introduction to the course. Second is second part of this first video is a refreshment of thermodynamics. So this introduction to the course is having a definition of diffusion, definition, and so diffusion, what the diffusion is, and with some examples the diffusion can be explained. For example, odor, which is agarbatti odor or fumes that is taken place of the one corner of the room is diffused into the other corner of the room. This is a good example for the diffusion, and so on. So other examples also explained in this introduction to the course, as well as, and the diffusion are is divided into two mainly and main different analysis, that is phenomenological diffusion analysis as well as atomistic diffusion analysis. The phenomenological means like diffusion can be analyzed with the help of a phenomena what it occurring, whereas in atomistic level, so it is based on the thermal atomic mobility. So if you give the temperature to the system, or if you increase the pressure of the system, there is an atomic changes the position in the change in the atoms. So that will be that will results in the diffusion. So this is also a one type of an analysis of a diffusion. These are the two main parts is explained in this introduction of the course, and the refreshment of thermodynamics is a basic concept, and the definition of the thermodynamics has been explained. For example, so first is system. What is the system is? What is surrounding? System plus surrounding. So what's the meaning of this one? And first and foremost thing is, so here we are sir explained about the first law of thermodynamics. Okay, so what's the first law of thermodynamics? That is given as delta U is equals to del Q plus del W. That means whatever the energy that is supplied to the system, that can be used for the increase in the internal energy as well as the doing the work. So this is the first law of thermodynamics that is explained in the first video itself. This is the second part of the first video, and its limitations. Limitation of the first law. So this is explained in the thermodynamics refreshment. Whereas second law of thermodynamics, second video is all about the second law of thermodynamics. So second law of thermodynamics says that so second law of thermodynamics says that second law of thermodynamics saying that it says about the efficiency, that is W by the work done to the heat supply. It's impossible to, the statement as go follows. It is impossible to construct a cyclic device which converts all the heat into work. That means, so it's impossible to construct its source. So it's work. So it's impossible to construct a device D, which will convert all the heat into work. That means there may be some part of the heat is being wasted or converted into other form of the energy. So there is a one term called as an efficiency comes into pictures to explain this type of efficiency comes into pictures with the help of a second law of thermodynamics. And second statement is it's impossible to construct a cyclic device which will take the heat from a low temperature reservoir to the transfer into high temperature reservoir without any external heat. That means it is impossible to, it is namely mainly based on your refrigerator. So extracting the heat from the given sample which is present inside the fridge, we need an external motor. So to remove the heat from that sample, we need a external motor that it will supplies a coolant across this one, and it will remove the heat and it is transferred to the surrounding. That's why we require an external aid of source to remove the heat from the substances. So one more is Clausius-Capron equation. Clausius equation. Sorry. Clausius equation that says that, in a cyclic process, whatever the heat supplied, reversible cyclic process, whatever the heat supplied should be equals to the heat supplied to the temperature is equals to the zero for the reversible process. Okay, so in an irreversible process, it's less than zero. So this is all about the second video. Whereas in the third video, the application of second law illustrating with the intermixing of the irreversible process has been stated. And equilibrium and third video, so fourth video is about equilibrium, stability, as well as the phase diagram of a single component system. So in this live interaction session, I will be telling about the phase diagram of a single component system with the help of a water phase diagram. And last is a third law of thermodynamics and the numericals on this one. I think you have all completed this all video series videos, 5 videos, and if you have any doubts, please let me know. I will be here. After this, we will be solving the some numerical problems on based on this video series, which will be helpful for your assignment problems. So this is all about the video lecture series that has been explained in this week. So next we will be moving towards the problem solving session. Okay. So in this problem solving, I have taken 5 problems. We will be starting with a problem 1, 2, 3 and 4, so on. So 2 problems, and first problem is this problem. Okay. Ideal gas at a temperature of 300 degrees Celsius, 300 Kelvin, has a volume of 15 liters at a pressure of 15 atmosphere. Calculate the first is final volume of a system, work done by the system, and heat entering or leaving the system, and the change in the internal energy, the change in the enthalpy when the gas undergoes. Two cases are given here. First case is reversible isothermal to a pressure of 10 atmosphere, and a reversible adiabatic expansion pressure of 10 atmosphere. So first we will be solving with the first case. It is reversible isothermal expansion. Isothermal expansion to a pressure of 10 atmosphere. So first we will write a given data. First given data is, so it is a T1, as we say 300 Kelvin. Okay. So V1 15 liters, and it's P1 15 atmosphere. Okay. So in first case he has given P2 to the 10 atmosphere. So P2 is here. So we will be determining first is volume, sorry, final volume, final volume, that is V2. So as we know, this is an isothermal expansion. It's a T2, T1 equal to T2 equal to 300 Kelvin. Then P1 equal to P2 equal to P2. Okay. So it is 15 atmosphere, and here it is V1 is 15. Okay. Then the P2 is 10 atmosphere. We need to get V2. So V2 is given as, just do 15 into 15 divided by this one. That's 225. Divided by 10, it's a 32.5 liters. Is the final volume. Then second one is given as work done by the system. done by the system. It is given as, so we know this is an isothermal process. The work done is W is equals to integral of 1 to 2 P dV, then nRT1 integration of 1 to 2 dV by phi. So this can be written as nRT ln V2 by V1 by substituting the value of n. So it will determine the n value, right? So to determine the n value, first need to determine the first thing is PV equal to nR. PV know it is 15 into 15 equal to n into n 0.0821 into T1 is 300, right? So from this calculation, n equal to 9.13 moles. So for this, from this n value, so we will be substituting here. It is work done by in isothermal process is given as, I'll write one more time, RT ln of V2 by V1. Okay, so that is given as 9.13 into temperature is R is 8.31 into 300 ln V2 means we have calculated the final volume, that's 22.5 divided by 15 V1. So this, if you calculate and you from the calculator, so this will tend to 944 joules. Sorry for the interruption. This will be like yeah, this one. Little bit, see again it is coming like this only. I don't know. Let it be. Okay. So I will write one more time. W is equals to 9244. I think my pad is not working properly. See? Okay, let it be. It's lagging. Don't know why. Okay. So we have calculated the work done by this one, isothermal process. Then is a heat entering and leaving the system. Heat entering or system. That is, in isothermal process, Q is equals to W. Why it is so? So internal energy will be a 0. One minute. So fourth option is given as in the internal energy. As I said here, it is a fourth one. Okay. So internal energy will be 0 for the isothermal process. Next is similarly for the fifth one is we are saying change in the enthalpy, that is delta H is also a 0. Okay, so first one is completed right now. So second is reversible adiabatic expansion, a pressure of 10 atmosphere. So I will be explaining. Okay, so that is second one, that is a reversible adiabatic process. Adiabatic process. First need to determine the first we will write given one more time, that is T1 300 Kelvin, T1 that is okay 15 atmosphere. Then next is given as, so V1 is also a 15 need to determine the, so first is V2. We know, so since it's an adiabatic process, we know the relation between PV in adiabatic, P1 V1 gamma equal to P2 V2 gamma. Simple. So need to substitute the values. There is a 15. So here it is, a tricky is gamma. We don't know gamma value. So he has given CV is equals to 1.5 R. We know the CP minus CV equal to R, that is CP equal to 2.5 R. Okay, then gamma is equals to CP by CV. Gamma is equals to 2.5 divided by 1.5, that tends to 1.66. So V1 is given as 15 to the power of 1.66. P2 we know, that is 10 atmosphere. Here it is V2, we don't know final value gamma. Then the V2 is given as 19 point something, 19.15 liters. Okay, so this is a final volume. Second is work done. Work done is given as, so we know the direct formula, NR divided by gamma minus 1, T1 minus T2. Okay, so we are not calculating the T2 value. First we will calculate the T2 value here in the side column. Sorry. Okay, let it be, it's almost right. So T2 calculated from the relation of whatever you want. So you can calculate the from the P value or the V value also. So I will calculate from the V value. So T1 V1 gamma minus 1. So T2 V2 gamma minus 1. Okay. We know T1 value, that is 300. It's 15.66. We don't know T2 value. We know this one, 19.15.66. So from this one, T2 value will be 255.5 Kelvin. So substituting these values, N we have calculated from the last example, that is A, that is 9.13 into 8.31 divided by 1.66 minus 1 into 300 minus 255.5. So this will be give rise to your work value as 5112.205 joules. This is a work. The next is heat leaving to the system, leaving or entering the system. That will be a 0 since it's a adiabatic process. Okay, so this will be the next problem. That is given as, so we have completed this reversible isothermal process as well as reversible expansion process at a pressure of 10 atmosphere when the system moves from 15 to 10 atmosphere. So here the multiple choice question will be solved, asked in your exams. What will be the final volume? That will be the easy one. And the work done, enthalpy and entropy. This will be the higher, and 2 marks question may be asked in your final exams. So next problem is the initial state of 1 mole of an monoatomic ideal gas is P is equals to 10 atmosphere, T is equals to 300 Kelvin. Calculate the change in the entropy of a gases. They have given the 3 conditions, that is isothermal, decrease in the pressure of 5 atmosphere, reversible adiabatic expansion to a pressure of 5 atmosphere, and a constant volume decreases to the pressure of 5. So we need to determine the entropy change in all the 3 cases. Let's start one by one. Let's start with a second problem. Okay. The second problem is, so he has given the P1 as 10 atmosphere, so T1 as 300 Kelvin. Okay. So starting, first condition is isothermal decrease in the pressure. Isothermal decrease in pressure of 5 atmosphere. Okay. So for that one, to determine the entropy in isothermal condition, so we have a nr ln of V2 by V1. Here in this one we don't know n value. As I said, it's a 1 mole, n equal to 1, and r we know we don't know V2 and V1. First, we will calculate the V2 and V1. We know it's isothermal process. P1 equal to PV equal to RT1. So P1 is 10, V1 8 not 8.3, it's 0.0 823. T1 is 300, V1 answer will be 2.4 liters. So please let me know the answers are correct or not. Okay, so it is liter. So need to determine the second V2 value. We know it's isothermal process. I'm losing this connectivity again and again. See, so I lost this again. Continue from the next one. So this is need to we have calculated the V1 value, that is 2.46 liter. Okay, so need to determine the V2 value. Similarly, P2 V2 R T2. So we know this is 5 atmosphere, and we don't know V2 value 8 point sorry 0821, and this one is 300, right? So that will be a V2 value. V2 is a 4.92. Since it is expanded, the volume is increased. So delta S value is given as NR ln of V2 by V1, that is given as 8.314 ln of, so it is 2.46 divided by 4.92. This is written as, this will be results in the Answer of 5.762 joules per Kelvin. Okay. So second is, so need to determine the entropy at a reversible adiabatic expansion. Adiabatic expansion. So the delta S is given as delta Q by T. That will be a zero because the heat change during the adiabatic process is zero, as I explained in the last example. Third one is a constant volume. Constant volume, pressure decreases to 5 atmosphere. Okay. So for this one, we have delta S is equals to NCV ln T2 by T1. So we know only T1 value, we don't know T2 value, then that's why. So we will be calculating T2 value first. That is P1 by T1 equal to P2 by T2. We know P1 value, that is 10, and this one T is given as 300. This is 5 and this is T2. So from this relation, T2 is given as 150 Kelvin. So delta S is equals to, since we know this is a monatomic gas, CV is equals to 1.5 times of R ln of T2 by T1. So for this, please substitute it. So it is 1.5 into 8.31 ln of, so we know T2 value, that is a 150 divided by 300. So you'll get delta S value as, obviously it is a negative value, 8.644 joules per Kelvin. So one doubt, so everyone can ask, this is a change, so entropy is a negative value. So according to the second law, third law, entropy and of a system should not decreases, it is increases or remains a constant at a equilibrium state. So it is given as, for example, but here we are saying a change in the entropy value. Change in the entropy value, that is, the system is moving from A to B, is showing a negative entropy. That means we are considering assuming that the system is moving from A to B, but actually it is moving from B to A. That's why it is showing a, if you calculate it from negative ulta, that means you will get it as 8.6. So this is a change in the entropy value, not a direct entropy of a system, isolated system. So this is all about the second problem. So I have given a problem 3. So it is based on the Clausius-Kaplan equation, estimating the vapor pressure. Please calculate it for 2 to 3 minutes. From this relation, everything is given directly here. So it is a ln P2 we need to determine, that is zero point 0.1 atmosphere P1, delta H is 40 kilojoule, .314. This is so again I have lost it. P2 0.1 minus delta H is given as 40, 8.314, uh, 373 minus 1 by 323. So calculate it, and the P2 you may get it is 0.6 atmosphere. Please let me know. So in this equation, in this numerical, what he is saying is, so material is there which is having a vapor pressure, enthalpy of a vapor pressure of 40 kilojoules. So a vapor pressure is material is, it's a vapor pressure is having zero point 0.1 atmosphere at 50 degrees Celsius. If the temperature of that a material is increased, or that liquid is increased to 100 degrees Celsius, so what will be the vapor pressure of that material, of that liquid at 100 degrees Celsius? That is 0.6. Obviously it should increase. So instead of that one, you can consider the a simple example of water. So if you are heating the water at lower temperature, it's having a lower vapor pressure, and if you increase that pressure, increase the temperature of a gas burner, so pressure will increases. And so this can be determined with the help of this equation, Clausius-Capron equation. So it will mainly depend, gives the relationship between the pressure and temperature. Hello. So that is a fourth problem that we now I am explaining. This will be related to the Clausius-Capron equation. According to this one, Capron equation. Okay. So in this equation, so what he is saying, let's start with the question. Estimate the change in the equilibrium melting point of a copper caused by a change in the pressure of 10 kilobar. That is a, he is already saying that the pressure is changed to 10 kilobar. The molar volume of a copper is 8.0 into 10 to the power minus 6 meter cube liquid state, and in the solid state it is 7.6 into 10 to the power minus 6, and the latent heat of fusion is given as 13.05 kilojoules per mole. Okay, so melting point of copper is We know that 1085 is the melting point. So here already he has given the change in the pressure, that is a delta P 10 kilobar. Okay, so next is latent heat. He has given already, that is 13.05 kilojoules. I have written in the form of joule per mole. Delta H he has given, and T equilibrium melting point temperature is 1085 plus 273 he has given. So this will be, please let me know the answer. 1085 plus 273, so 1358. So this will be the 1358, and here it is 0.4 into 10 to the power of minus 6. Substituting all this, so we can get the change in the estimated change in the equilibrium melting points. It is 10 kilobar. That means need to calculate into 10 to the power of minus 9 Newton per meter square. So bar means 10 to the power of 5. 10 into 10 to the power of 5. That's kilobar he has given. 10 into 10 to the power of 8. Here I will write it. dP is given as 10 into 10 to the power of 3 into 10 to the power of 5. Okay. So here it is all the concluding 10 to the power of 9 Newton per meter square divided by dt. So delta H is given as 13050 divided by, so it is 1358 into delta V value 0.4 into 10 to the power of minus 6. So what will be the change in the equilibrium melting point? Let's calculate that one first. So 130 divided by this one. Sorry. So this one. Okay. So answer is 42 Kelvin. So this will be a very useful data during the melting in the controlled atmosphere. This is very useful. So if you have an arc melting, a vacuum arc melting, or some other controlled atmosphere of melting of some alloy, so if you want to melt that alloy at a lower temperature, so we can need to, so what are the parameters that we need to change it to decrease the melting temperature, equilibrium melting temperature? That is delta T is directly related to the delta P if this is a constant. So if you want to decrease this uh, equilibrium melting temperature, or so it is a change in temperature, that is a T2 minus T1. So by keeping this one, so if you want to change the T2 value, need to change this one value, and if this differences is too much, and this, okay, so if you decrease the pressure, so this will be also decreases, and at lower melting temperature you can melt the alloy. Am I correct? So if dp is changes less, and this is also less. Okay, so if you want to melt it at a higher lower temperature, then if it is in a 1 atmospheric pressure, if you decrease to zero point 0.1 atmospheric pressure, so again here it is T2 is, for example here it is 1085, so this will be lower than this one. Exactly, yeah. So this is the case. As sir said in the video lecture series, if you go for the higher altitude, the pressure is very low, and there the boiling of an rice is very difficult, because a boiling point of an water is reduced. That's why it's very difficult. Similar, yeah. So this is the main intention of this problem. Next one is a very important example, and this is many times asked in the papers. So this is the water phase diagram of a water PT diagram. So PT diagram of a water it is having. So these lines are explained on the basis of Clashes Capron equation. As the sir said in the video series, this is having a negative slope as well as negative slope, because the change in the volume, that is delta V value, so change in the volume from ice to V is negative. That's why it is reducing one, delta P by delta T. So in case of other two conditions, that is water converted into vapor is having a positive volume change, that is delta V, as well as ice changes to direct vapor. This is also having a positive delta V value. That's why delta P by delta T is having a positive. The slope of this one is also positive. That's why we are having a this type of okay. So then, if you want to, already in the video series, we know that at a triple point, at this point, we know that GT diagram looks like this. Sorry for this. Again, same mistake. Make a single point. Yes, this will be good. And again, one more. Array. Next time I will make ready-made images and I will come. Okay. Okay. Yeah, this is better. So this is solid, liquid, and vapor. So below this one, a solid is stable, whereas above this one, a liquid is stable. This is T equilibrium melting temperature. So when this line is moving from solid to liquid, below this solid is stable. Similarly, so it is shown here G versus T, and whereas about equilibrium melting temperature, a vapor is stable. Similarly, if this is at a pressure of P of point atmosphere. Okay, so if you increase this pressure to P 1 atmosphere, so what will be the GT diagram? Let's see. So if we draw a straight line here, so then GT. Okay, so here P is equals to 1 atmosphere. So what will be the first? So this, if you extend like this, it will intersect here, and here it is there, and we have to increase this one to increase this one. Okay, so I will use different colors so that it will be useful for you guys. Color, in color, I will use black, better. Okay, so I will extend this one, and I will extend this one. Okay, so first is solid is stable. Okay, then before intersecting here, uh, solid and the vapor is there, that is intersecting at lower temperature. See, at this temperature, so need to okay. Yes, this is solid and this is gas or vapor. Again, it is line is intersecting. This line is intersecting in the liquid and vapor gases. So finally, yes. It should come like this, and it should meet. Okay, so this one, it should meet at lower pressure. Again, here it is. Yes, I got it. Here it is there, and here it will goes like this. Okay, so this is gas. So liquid is not at all meeting to the, okay, solid. This is considered as this. Okay, I got it. First, I need to refresh this one, reframe this one. I have missed one thing. Sorry for this one. Sorry for the inconvenience that I caused right now. First, solid is limiting to liquid here. So need to get a liquid first at this temperature. After that, a solid is meeting to at higher temperature meeting to this one. Again, it is meeting to here. Okay, the gas is there. Solid is meeting at higher temperature. Then from here to here, it is there here. One more time, I will try it, man. Don't worry. Again, I'm making same mistake. Okay, consider this. This one is liquid and this one is gas. Gas is stable. See this one and this one. Here it is T1. Again here it is T2. Here it is T3. See here T1. Here it is gas is there, liquid. First it is T1 is meeting. Again it is meeting solid plus. Here it is T2 gas is meeting here. T2. Again finally it is meeting at here T3. Simple. So first initially I missed this point here. So that's why I got confused. Okay. Yes. So this is at different temperature. Again it will be a different. So for example, at below temperature here at this temperature, it's very easy. No intersecting point, but here it is one intersecting one T temperature is there. This one is meeting here. It is going like this and it's going like this. Okay. So that is all our vapor state. Vapor is first we have to draw a vapor curve. Okay. Then afterwards, solid is meeting to liquid. That is upper state. Here it is. But it should be this one will be the T value, T1 value. But the Gibbs energy of vapor is always lower than that of the solid and liquid. See. So if you have any doubts, please let me know. So we will solve one more problem about this one. So I have a little bit problem in drawing the diagram. Isomorphous diagram. You know all these things. So if you have any doubts, any problems regarding anything, please let me know. So I have observed one homework questions that is, so we can discuss here a little bit time if time is there. In the video series, sir uh, explained about process A to B is irreversible process. Moving of this process is irreversible. So that's why they have considered so sir has in the this explained about the process A to B is a irreversible process. So that's why they have carried out this process in a two steps. There is a reversible adiabatic process. So A1B is so two step process. Okay, that is converted into A21 adiabatic reversible adiabatic process. Consider the two reversible process adiabatic. The second one is 1 to be reversible isothermal process. Reversible constant pressure process. So instead of that one, we can carry out this A to B into two reversible two different process, that is constant pressure and volume. So constant pressure as well as constant volume process. Okay, so that is considered as to A22 is a reversible constant pressure process. And 2 to B as constant volume process. Okay, so in this one we need to determine the entropy change. So during the constant pressure process, so delta S can be calculated with help of CV ln T2 by T1 plus R into ln V2 by VA. Okay, so whereas constant volume process, so we know CV is equals to ln of T2 by T1. So if we consider the adiabatic process, this entropy, calculating entropy will be 0, but the answer will be change in entropy will be constant, same in both the condition. If you consider adiabatic process as well as isothermal process, again you can multiple variation will be there. So you can calculate, we can consider the adiabatic process also here. We can consider the reversible isothermal process as well as another combination of constant pressure process instead of adiabatic. So but answer will be same. So do you have any other doubts regarding with these things? Please let me know. So I think I can explain with one more time. So this white screen. So sir has explained about the one problem on this one. A reversible process A to B. So it can be calculated determining the entropy, change in the entropy value. For the irreversible process, it is difficult, and that's why we are converting into two reversible process. One adiabatic process and one constant pressure process. Delta S due to adiabatic plus delta S due to constant pressure process. Okay, so that's why so we can do one more way of doing this is A1B. So we can calculate with another thing 1 to B. A to B, that is, sorry, here I will write A to 2 is constant pressure process. So 2 to B is constant volume process. This is PV diagram. Sorry to explain this one. This is PV diagram. Constant volume process. Okay. So if we calculate the okay, so first we will be considering this constant pressure process. So delta S will be okay. This will be the better. Okay. CV LAN T2 by TA plus R into ln of V2 by VA. So this is uh, by constant pressure process. Constant second is constant volume process. So delta S is given as CV ln of T2 by TA. Okay, so this is because V constant volume process V2 by VA is 1, that is ln of 1 is 0. This term will be V0 for the case of constant volume, and we will be getting for this delta S only by changing the temperature. Whereas if we consider the isothermal process, this will be a 0, and you need to calculate the only with the, in terms of volume change. Okay, yeah. But in adiabatic process, a whole entropy is 0 because heat exchange with the system, with the surrounding is 0. There is del Q by T is 0. Del Q is 0. That's why entropy change is a 0. The entropy remains constant in the adiabatic process. So if you consider the different multiple reversible process, then also you should get a same value of change in the entropy. Then this is, if you consider this is a delta S1, this is delta S2, the total delta S is given as delta S1 plus delta S2. Okay, so this is all about the another problem. And sir has also explained about the two different type of entropies present in the system. Okay, yeah. So there is a configurational entropy. Two type of entropies are there: thermal entropy entropy and configurational entropy. So configurational entropy, the thermal entropy is mainly due to the when we supply the heat to the system, the atoms will vibrate its own mean position. So that results in the randomness in the system, that is called as a thermal entropy. That is a disorders is caused this one, and this is still due to the external temperature. The atoms will move from its mean position. This will result in the randomness in the system. That is nothing but the thermal entropy. So configurational entropy will comes into exist when we add the other elements to the host element. The substitutional elements or another foreign elements will occupy the interstitial or the substitutional sites of the host material. Then it will result in the different combinations of atomic positions. This will result in the configurational entropy. So this is mainly due to the addition of impurities or the allowing elements, other things. So please let me know if you have any doubts, anything about this one. So as I explained previously, these are the two books. So for our my experience, so whatever our professor is teaching in the online nptel videos, that will be sufficient to get the gain enough knowledge about the diffusion in the multi-component solids. This is a 16 week series of video lectures. You will get not only get a certificate of nptel, you will get a good knowledge regarding with diffusion in multi-component in solids. You will be very curious to know how the diffusion is occurring throughout the sample just by giving a temperature. So how this analysis will be carried out? So if two elements are there, if you diffuse it, Okay, so if you know, if two elements are there, if you combine this one, there is a diffusion occurring between these two elements because of the concentration gradient or chemical potential gradient, and this can be analyzed in a different manners, different methods. That's the Boltzmann-Matano method, Kirkendall methods, and many methods are there, and each and every methods will be explained in detail in this video series, and you will get enough knowledge and a very good knowledge and very systematically performed, well structured. So it's a well structured course that will be helpful for gaining a knowledge regarding with your basics as well. So this is mainly first video, 2 weeks series consisting of thermodynamics related problems, thermodynamic related concepts that will be helpful for this concept will be useful in the upcoming division explaining concepts. So that's why so there is a refreshment of thermodynamics should and must and necessary, and it is useful to everyone. In your limit. So please let me know if you have any problems and a doubt regarding with these things, so that I can be solved with the preparations. And this session is it may be useful to everyone for solving the doubts, clearing the any problems in this division in multi-component solid subject. So most of them will think that this subject is a little bit tricky as well as difficult, but a correct understanding will helps to can help you to make a cakewalk in this subject. So thank you all. Thank you for giving an opportunity to share some enhance my knowledge also, and thank you for discussing. And so if you have any doubts, please let me know, and I try to solve the I can try to solve those problems with this platform. Okay. uh, Next week, I think you should submit your assignment by this week, right? By Wednesday, right? Yeah, upcoming Wednesday you should finish your first assignment. I think you got your second week video series. Please go through those videos, and if you have any queries regarding with the assignment 1 problems, please let me know in the next upcoming interaction session. So we will be solving those problems, as well as along with that one we'll be solving other problems also, and which are related to the week 2 videos. If I don't know any questions, if I'm not able to answer your questions, I will note down those questions and discuss with my other professors, and I'll let you know in the next upcoming sessions. Okay. So I will conclude my this session for this week, and we will see in the next week. Thank you. Thanks a lot.